I'm excited. I got my PhD from the University of Washington. It was interesting getting my PhD there because at the time there wasn't as much interest in scientific computing and visualization there, and I wound up going to Los Alamos during the summer to try and figure out what who I wanted to be and who I was, and I fell in love with the place, and I've been there for 17 years. Some people say to me, well, how could you be there for 2 decades? And it's like my job changes every day. That's what's so cool, because I get to work with all different sets of people and do all sorts of different things, and so I don't feel like I'm in the same job every day. When I started, I want to go to the passion first. I have a passion about science. I think it's critically important in many, many ways. I think it's one of the key aspects of being human is trying to understand what's going on. And so I want to enable scientific understanding, and I was struck when I went to the lab that there was a lot of simulation work going on. It was a new area, new way of thinking about doing science, and there was just a crying need for how do we actually understand what's coming out of these massive simulations. And so at the time I started working, I said, okay, well, we need a tool so that people can do this. I started the project called ParaView. It's an open source large data visualization tool where there was a few people at the time, and it's grown up over the years to be used around the world at the supercomputing centers and enables a lot of science. Recently, I've had more leadership roles in DOE, including planning for the next big machines and working with the White House on issues about big data and high-performance computing. There's a lot of people really want to understand what these relationships are with big data and how it affects the world. So I like metaphors, and so I think that one, I thought of, what are my current challenges? And these are my challenges that I've had since I started. I think it's like a car. Essentially what we're trying to do is we're in a car, we're driving up a steep hill, and we need to keep changing the car while we're driving. We need to keep making it faster and better and super. And meanwhile, and the interesting question to me is people keep saying, but what about the user experience? Right? And you're sort of like, you imagine a guy strapped on a rocket, right? And you're wondering what his user experience is, and you're kind of like, okay, well, we'll keep improving that, So, every 10 years, there's 3 orders of magnitude increase. Since my career, I came in, we were doing terascale. 10 years later, it's petascale. Ideally, we'll be at exascale in 10 years. I think that's really difficult to understand. I like the Empire State Building that somebody used. This is a lot of Empire State Buildings. Just kind of, the way we're doing that is there's fundamental changes, just sea changes in the software and hardware industry that I also think are difficult to convey to the scientific community. Physics changes every 100 years. We're changing every 2 years. So it's really difficult to explain. It's like, no, it's not the same. But, in the course of my career, we've gone from shared memory machines, started out with these SGIs. People loved them. They weren't going to let them go. 5 years later, it was all clusters, and the SGIs were gone. Then it was, oh, we got massive multi-threading. Then, thank you. Keep going. It's just kind of, now we're looking at data-oriented stuff. And that's really hard to explain. Hey, there's $1 billion industry focused around data-oriented stuff. And everybody's like, what? What happened? We're HPC. Like, well, the train has left. We're going in another direction. And while we're doing all that, we're changing all those things and we're getting going, we need to advance the fundamentals, because fundamentally it's about how somebody understands what they're looking at and really thinks hard about, did I get something out of this visualization? So in terms of a current challenge in HPC, and people have alluded to this, it's shepherding this fundamental change from sort of, I'll save all my data and I know what I'm looking for and I'll get to it later, to sort of automated techniques and new representations where you can go look at these things, but you're doing this stuff up front. And that's a big change I don't think people understand either. You're really, in the past, what we sort of sold, and I think it's bad, is that we sold, hey, you can get anything you want out of your data, just save it to disk and you can go mine it later. And it hasn't changed, but in situ really brings it home, that you need to know what you're looking for and need to know what the question is you're asking, before you start your scientific experiment. At CERN, they know they're looking for the Higgs, right? I mean, they're not looking for 10 other things. They're looking for the Higgs, and they set up their experiment and do their analysis in that way. Right. 1 minute. All right. I wanted to get to this. I do believe that one of the things we need to do as a visualization community is really understand what these data-intensive approaches. There's a lot of investment there. We need to do it. But I really want to get to this last piece, which is that I think we need to take a sampling-oriented view. There's a budget. I get it. There's a budget of what I think people don't understand is when you do visualization or scientific analysis, there is a budget of what you can do. It's out there. It's a budget of humans. It's a budget of computers. It's a budget of whatever. And you have to decide, okay, what am I going to do? And so there are techniques in stats, including sampling and experimental design, that say, hey, I'm running a scientific experiment. I want to know something. Well, how do I sample the data, the input streams, all these things so that I actually get the answer I want? What is the uncertainty associated with that? What's the bias associated with that? How do we show that, and how do we sort of pull that all together? That will improve our science. Thanks.